This is lecture 13, the final lecture for chapter 4, and the final lecture before the midterm in terms of material. Now, what I want to do in this lecture is just talk a little bit more about chapter 4, 23, equilibrium problems, do a few more examples, and then at the end of this lecture, I'm going to do a quick overview of what to expect on the exam. So you should hopefully have downloaded your example 13 worksheet, and that will have these problems on it. Otherwise, you can just follow along. So now in this example here, we have member AB, and it's a bent rod, but notice that it's square, and it's placed over a square stock bar. And because of the square shape, it's not going to freely rotate about the z-axis. But because it's not round, that means it's going to be able to support a moment about both the x and the y-axis. And actually the z-axis, it's going to be able to support a moment about all three axes. In terms of a force, the only thing it can't do is support a force in the z-axis. So it's a little different than what we've done. Now this problem in particular is easy because it's not really asking us to do a lot. For example, you're told, now again, whenever it says smooth, that means that there's no friction, which we haven't dealt with yet anyway. And it tells you that you have this down at F, there's a 45-pound force in the negative z direction, and all you want to do is calculate BC. So let's go ahead and look at that problem. Okay, so here we have the drawing. What I've done is I've, again, always make a good free body diagram. I've emphasized that it's free to support a moment of the x, about the y, about the z, and support a, y, ax. We know az is 0 because it's free to slide up and down on here. And so we have that. Now, all we're asked to find is TBC. That's it. So with that, you can, there's a short problem because, again, you only ask for something simple. And this is an important concept because sometimes on homework or even on exam or quiz, I'll ask for something specific. And I've seen this in classical classes where someone will work a whole bunch of extra stuff and they don't need to. And they'll end up getting more extraneous information, or they'll be solving for values that I'm not asking for. And though that's nice, it's not going to help you with the problem. So you just be aware of that on the test, just solve what I'm asking for. Now, in this case, we know that we have a negative 45 pounds going down. And we know that here, this can't support any force in the z. So the only other part of the system that's going to be able to offset that 45 pounds going down is going to be the z component of this, right? Because we don't care about the x or y component because it's pure z. So we just want to get that z component. So if we do that, we go ahead and find our r vector going from B to C, then that's essentially equal to r with the location C minus the location B, and that's going to give us negative 12 in the I plus 4 in the J plus 6 in the K. Okay, and that's just our simple dimensions if we went from B back to C. Okay, I don't think I labeled the 12 here, but that's the distance along this x-axis. Go back to the picture if you don't believe me. So if I square root everything, I get a magnitude of 14. So what that means is that if I draw the unit vector lambda for BC, it's going to give me 12, negative 12, 14ths I plus 4, 14ths J plus 6, 14ths could reduce that to 3 sevenths, 2 sevenths, 6 sevenths if I wanted to. But the important thing is that I have this unit vector. Now I know that the force in the I know that force BC vector just equals the scalar BC times lambda BC, and I know that the x component FBC, C component is just going to be equal to this times the BC Z. So another way to, sorry, a little screen. So another way to think about it is that the F in the BC in the Z direction is simply equal to FBC times 6/14. Okay, and that's it. So if that's the case, and I sum my forces in the Z, then what do I have? I have 6/14 minus, I have 6/14 FBC minus 45 is 0. And so if I solve for that, it's basically 45 times 14 divided by 6 gives me 105.0 pounds. So there, I've solved for the tension. Force BC, tension BC, same thing. But so the tension BC equals, not the vector, sorry, we only wanted the scalar. So tension BC is 105.0 pounds. So simple concept, but you see how that worked out. So all we cared about was the Z component. So if you think of the Z component going straight up, it has to be offset by whatever that component is there. And that's the end of the problem. So not so bad. So go ahead, go back. So here's another one. Now, in this case, you want to be able to be sure that you look closely at how the actual geometry is. And so in this case, you have this rod A Beth, and Beth. It's supported by bearings C and D. We know that bearing D cannot support any axial thrust, so, and that's probably just not going to carry anyway, because if we look at the forces, all the forces are in the Y direction or the Z direction. There are no forces in X, so it doesn't really matter. But that's a good thing to note anyway. So we want to know TAH, or the tension in AH, and the reactions to C and D. So if we look at that triangle AHB, or BAH, or HAB, whatever you want to call it, you can see that that's a equilateral triangle, because you're told that AB is 250 millimeters, and the distance HB is also 250 millimeters. So if two sides are 250, the third has to be 250. So that's going to give us an insight as to the angles that we need in our free body diagram. So let's go ahead and solve this. So here we have our diagram, dimensions in millimeters. And here's my triangle. So I've just drawn it so you can see where the dimensions came from. So I have no dx and cx are 0. So I have my cy and cz, dy and dz, and my force at F at 400, and so forth. So again, just like the other 3D problems of this nature, we know our governing equation. If we sum the moments, C is 0, then we know that that's going to be our H relative to C crossed with the tension DH plus our D relative to C crossed with D plus our F relative to C crossed with the force in the J direction, and that all equals 0. So that's my governing equation. I chose to take the moments about C. You could have done the same thing. This could have said moment about D, in which case this would have been H relative to D, this would have been C relative to D, and then F relative to D. But we chose C. So live on the edge, do it the other way if you desire. Either way will work out fine. So now we know our equation, so we need to know what are our distance vectors. So we know that if we go from 8r h relative to c, that's going to give us negative 50i plus 250j. We know that our d relative to c is just equal to 300 in the I. And we know that our f relative to c is just equal to 350i plus 250k. So again, we're always going from C to the force. And that's where we get these numbers from. All right. So the last thing we need before we can put together our matrix is the tension D of DH. And so I have, sure why I wrote, or AH, I'm sorry. I don't know why I wrote that. So tension AH is going to equal to tension AH times, and then so if we think about it, AH is going in what? The negative Z and the positive Y. Now because that's a 30, 60, 90, I'm sorry, because that's an equilateral, this turns into a 30, 60, 90 triangle. So if we draw this here, then we know that our distance in the Z is just going to be the cosine of 30 times AH, and our distance in the Y is just going to be the sine of 30 times AH. So our AH just simply becomes sine 30J minus, because we're going the negative Z direction, cosine 30K. And that's it. So, and we know by now that this is 0.5, and that's square root of 3 over 2. That's what those are equal to. So let's go ahead and set it up, just like before. So let's go ahead and write it out. So voila, there it is. Sorry if it's not perfect focus. It's this pesky overhead camera sometimes doesn't focus perfectly. So here we have our H relative to C times the AH. I don't know, I'm sorry about that. This should have been an A up here. So AH. And so there's our respective R, there's our P times half and negative root of 2. And D relative to C, there's the distance, and then the two reactions, dy dt, and then F relative to C, the distances, and the value of negative 400 in the J. So once we have that, then again, we're just going to separate the I, J, and K components. And for the I, we get negative 216.5 of times T, D, T, A, H. And that's going to be plus 1.0 times 10 to the 5th. That equals 0. So we get T, A, H is equal to 462 newtons. So then J, we're going to use it to find dz and dy. So we do that, we get negative 43.3 of TAH minus 300 dz. All that equals 0. And for K, we get negative 25 times TAH, tension AH, plus 300 dy. And then also minus 1.4 times 10 to the 5th. That equals 0 also. So if we subsequently solve by putting AH into here, we get a DZ value of negative 66.7 newtons. So DZ is going the opposite way we guessed, which was positive, so it's going negative, and that's why I would guess positive. That way the negative is both telling you it's the opposite and it's going in the negative direction, so there's no uncertainty. And lastly, dy is 505 newtons. So if you go ahead and sum the forces in the y to 0, you get cy plus 505 plus 462 times the 0.5, because that's the sign of the tension AH, and then also minus 400, all that equals 0. So cy ends up being a negative 336 newtons. And if we do the same thing, sum of the forces in the x to 0, I'm sorry, sum of the forces of the z to 0, we end up with cz minus 462. Now that's times the square root of 3 over 2. And that's minus 66.7 equals 0. So C sub Z, or the reaction at C in the Z direction, is 467 newtons. There you go. So you have everything. Again, on a test, I would encourage you to box everything, make sure it's very clear. Don't make me have to hunt for your answer. It makes me grumpy, so you don't want that. Okay, so that is an example. I think it's pretty indicative of the level of difficulty of an exam question in terms of what you'll have to do. So if you understand these well, then you should be okay. I'm going to try to make you think on the test, not just have you rotely repeat what I've taught you in a question that's exactly the same, but as long as you understand the concepts, you should be fine. So going back, we have one more example I'll show you. And in this example, I'm going to walk you through it without writing it all out, because you've seen it like this before. The last one in the last lecture. Now, here you have the bent pipe, ACDE. And so the bent pipe is connected by ball and socket joints at A and at E. And you have single force 640 newtons down, and then you have this tension DF going up. So we want to figure out what DF is. That's all we're asked for. So notice how we're not asked the reactions at A and E. We're only asked for that. So that's going to pretty much tell you that you want to have a line, because in order to get rid of those 6 unknowns, because just because they're not asked for doesn't mean they don't exist in the problem, but to get rid of them, so you don't have to deal with them, you can draw a line, take the moment about the line, and voila. So let's look at that. This is out of your book. I think it's problem 138. So here we have our schematic, or I should say my free body diagram, sorry. And so I've drawn in DF going up here. I have my reaction at E, reactions there. So I know that I can draw a line that goes between these 2 points. And there's the line. And again, like I mentioned in the last problem, you can make AE or EA. It really doesn't matter which direction you go, but you're going to want to take the moments about that line. So down here, you can see that if I go AE, I chose, it's going to be 480I, 160J, minus 240K, just as I written, 480, negative 240, positive 160. And that's over the magnitude 560. So this turns out to be 48 over 56. So if you divide by 8, what do you get? 6 and 7. So it reduces. And a lot of these problems out of the book, they reduce Just nice fractions. So we have our unit vector, and then of course we need to figure out each of these forces. So we have to go from the line to the force. So in that case, if we go from A to B, or B relative to A, that's just simply going out 200 in that direction. And that 200 was labeled on the original drawing if you go back. In terms of going from A to D, you do the same thing, 480i plus 160j, just go all the way out and up. Now, I could have gone just this direction here, so I could have made this, instead of 480i plus 160j, this could have been just 240k, and it would have worked out exactly the same. So you could try it both ways if you don't believe me, but you could have done it either way. So now that I have that and that, I need to figure out what is my tension dF in terms of a vector. So I know that if I take dF, just like you've done before in chapter 2, so this, I'm going to go through this fairly quick because you know how to do it. You multiply the scalar value through each of the respective vector directions, and then there's our governing equation. So the moment about AE, lambda AE, dotted with RD relative to A, crossed with TDF, plus lambda AE, not crossed, sorry, it's a typo. So glad I caught that. It's definitely not a triple. There you go, dotted with RB relative to A, crossed with F1. And that's it. So we go ahead, we can set them up just like this, just like anything else. We have our 6, 7, just put them in there, and we do our cross product like we normally would. And again, if you need practice doing it, do it. If you take my word for it, also, and it's always good to check, because I've been known to make mistakes on occasion, just to prove that I'm not flawless. I do everything perfectly, but I wouldn't want you to get a false sense of it. So anyway, all right. So here we are. This is what's happened after I've done the cross product. So I have 6 7ths. This is the I component. And so because the zeros, some dropped out, so I have that. And then plus 2 7ths. And so here, actually, I'm sorry, with the X, there was no 0, so we got the whole thing. So we got that, plus that, minus that, minus that. And so that's everything that came out of those. And all of that equals, should say equals 0. And then subsequently, all of this equals 0. So basically this reduced to this equals 0. And so when you finally get done with putting everything together, notice this and this cancel, so you just have the 160, and then negative 3 7ths times 200 times negative 640 gives me that value. So finally I end up with this, and I get my value of 343 newtons. All right. So from there, that's all I have to do, because all it's asking for is that tension. There are no reactions. So had this gone on farther, we would have summed the forces in the X, Y, and the Z and solved for our subsequent values. So you can see there's two main types. There's one where you're only finding the tension and you're summing moments about a line. And then there's also where you're going to sum the moments about a particular point, and then you're going to find those subsequent reactions. Obviously, the latter is a little more time consuming, but in terms of the math, it's pretty much the same. So those are the 3 examples I want to show you. And last thing I want to mention is just a brief discussion of the exam. Now, normally in class, I'd have a review and people would ask questions. So I encourage you during office hours, if you have specific questions, to come and ask those. But what I wanted to say briefly was I did post on Canvas a study guide. So look under that under week 4 materials. And what that does is it lists not only does it list the methods of each different way, but use that also not only, but what I meant to say is use that in combination with the learning objectives, which I posted under each week's overview. So the learning objectives will kind of give you an idea of my expectations. And then the study guide tells you specifics of how to solve. So for example, in chapter 3, it says know about a point, and it gives you step-by-step instructions, knowing about a line, step-by-step instructions, and so forth. And I believe there's no typos in that. I may, as I recall, an older version of it had a unit vector that the letters might have been reversed, but I'll double check that. And if you see something, let me know. So as far as review, the test itself will be 3 to 4 problems, similar to homework. Generally, they're in increasing levels of difficulty, so the first one's a little easier. Now, normally I would give an exam. It'd be a 50-minute exam in a class period, closed notes. But I'm not going to say closed notes because I can't control it. And so it's obviously open notes, but not open people. So it's really imperative that you don't discuss the exam while you're doing it with any other classmates or anyone else for that matter. It is not good if I do determine that you've cheated, then you basically fail the class and there's other repercussions. So it's just not worth it. The test should not be that difficult. You'll have more time for this exam. I'm not sure exactly the exact format. I'll probably be sending an email out to you guys letting you know how I'm going to proctor it and facilitate it. It'll probably give you a 2-hour window to work within and give you X number of minutes to do it. So I'll try to make it as reasonable as possible. So I would encourage you to look at my past exams. It'll be, it won't be exactly the same given the new way we're doing it, but at least it'll give you an idea of the level of difficulty that I expect. So one of the things, a question I get oftentimes is how do you study for the test? So everyone I know has different learning styles, and unfortunately this online does not necessarily facilitate everyone's learning styles, but what I would say is the best way to understand this class is through repetition and understanding the problems. So if you understand the homework, there's no sense in redoing it and going through it because you've already done those problems. So all you'll do by redoing the homework is get really good at doing those problems. And I can guarantee you none of the homework problems will be on the test. So if you want extra problems or practice, what I would do is look for problems in the book that are similar, and there's quite a few that are very similar to what you've done, and work them out and see where your spots are. So now, granted, you'll have time, you'll have notes, but time will still be against you because you only have a window of time to do this exam. So you want to understand the concepts. You don't want to try to learn the concepts on the day of the exam. That's not good. Now, I did in the past give a cheat sheet, so to speak, a sheet of notes, but for the most part, it doesn't really help on the test as far as using it. What help really comes from the act of writing it down. So if you write the stuff down, it might solidify it better in your head. But again, you have to do with what has worked for you in the past. So that's about the best advice I can give on how to study. Practice, your weaknesses. I will say that the quizzes have been a little on the easy side. So that last quiz, that second problem was a little harder, but that still wouldn't rise to the level of an exam question. So just be ready, study, and I'll announce what's going to go on with the exam. So I will be posting the next lecture with chapter 5 before the exam. And so chapter 5, we'll start talking about centroids, and then we'll move on to chapter 6 and talk about trusses. So hope you enjoyed this, and I'll see you next time. Thank you.